Thank you. So yeah, I'd like to use Haskell everywhere, right? So today's talk will be about Yolc. Actually, my company is Superfluid. Our protocol is called Superfluid. Yolc is a project I just started recently. I want to use Haskell to build smart contracts on Ethereum at the moment. So very glad to be here. It's my second time to Lambda Days, and thank you for coming just right after lunch. So what I will talk about today is that I'll first talk about what's my motivation for the Yolc as a compiler for building smart contracts. I'd like to also dive into the approaches used by Yolc. I will show that how I represent programs using categories, but I'm not going to talk about category 3. No, I'd like to just talk about that echelon doesn't show through diagrams. So I'll just visually show what are the categories actually used behind Yolc. I'd like to also talk about the deep embedding programs in Haskell or EDSL. I'd also show a demo using linear types, a safety feature I experimented to provide something called data versioning, which unfortunately in Ethereum world, there's a lot of issues with too powerful, let's say, quote, programming model. Somehow we need to restrain it. So this is one way that I find maybe can prevent some class of error. In the end, I also interleave with a few demos during the talk. I need to watch time though. Also the next step of the project and how to get involved if you're interested. So let's first talk about the motivation of the Yolc as a project. So for me, the most important part is practice. I would like to bring the expressive type system of Haskell to the world of Ethereum smart contracts. So that's kind of my foremost important priority. Also, I'm interested in theory also. I'm very interested in linear types in general and how to encode some safety models, such as things like linear time temporal logic to see if it's possible, right? But I'm not a theoretician, so I'm exploring the space instead. So lastly, since I'm also co-founder of Superfluid as a company, so there has to be some business value. So I'd like to doc for the Yolc in the project Superfluid so that this actually can lead somewhere eventually. So let me start with an overview of my approaches. So just a general overview of the pipeline. So it starts all with Haskell code. So as I said, it's an embedded DSL, so it's all in Haskell. But I have a couple of different ways of how to embed that. But my approach is slightly different than many of the EDSL, which probably start with a Lambda expression in the data constructor. I start with a category. So everything converts to the category. I don't do compiling to category, but I just convert, right? I don't know best word to say that, but it's convert to the Haskell code to the category. Now I have different interpreters for interpreting the category into different pipelines. So of course, the red arrow is the most important one. So I actually target the category to something called a Solidity U/U. If you don't know about that, I will explain a few slides later. So it is an intermediate language that has tooling supports it, which you can eventually compile it to the Ethereum virtual machine or EVM, the bytecode of that. So the tool is called a Foundry and SOLC, which is a play of a word. Of course, I use Yolc versus Soak or a Solidity compiler or Yolc, so it's a play of a word. I'll show the demo just right after these slides, but I also have a couple of other evaluators, such as directly evaluating the category so that you can test in Haskell natively, some sort of emulator, and then I can just emulate the category without in runtime, so I can test in Haskell. Lastly, I can also easily write some other interpreter, such as Graphics visualizer of what's the visual presentation of the category, and I can also do some serialization if I want to share with the other EDSL, not necessarily in Haskell, right? So that's all possible. So that's the general pipeline from left to right. I'll show you the red arrow. I'll show a quick demo. End-to-end Ethereum toolchain, right? So as I said, I want to be, my primary focus is practicality. I want to actually build it something. I want to build something. Yeah, I want to make it end-to-end work. So just a quick disclaimer, there's still a lot of things work in progress and not feature complete yet, but whenever I have time, I try to do a little bit progress. So let's walk through the project structure. I usually doing Emacs, but for this demo, I'm just using the Visual Studio. Hopefully it's big enough text. So the starting, well, this is a typical Haskell project, right? So there's a Cabal file. Since I also end-to-end integrate with Ethereum tooling, there's something called Foundry. So if you search Foundry Ethereum, you should be able to find that link to that. So I have two project description. One is for the Haskell Cabal file, and the other is a foundry.toml. The source file is all in Haskell. It's all module listed here, right? So I have a where is my module list? I'm confused. Oh, here. So we have a ERC20, I have counter, demo, a module of raising funds. But the starting point, entry point will be a project. So a project defined build units. I can describe their object and deployment type. Is it singleton contract or is it contract that's split into multiple units? Is it upgradable or not upgradable? But that's very Ethereum specific, right? So you can actually upgrade the contracts, which is very controversial, I would say. So that's a build unit, and typical module would look like this. You describe in the object level what function you are exporting, and for each function, you can then write. Either you can say it's a pure function, or is it has some effect, such as getter, like static function, or is it something can do more, right? So I'm going to show you the. So this is how the project look like, but I'm going to just show you how I test in the Foundry, right? So I can go to the example demo and say Forge. Forge is the tooling from Ethereum Foundry. It's so I just say test. I believe test. That's it. No files changed. Completion. Okay, all passes. So how about let's change something here? So I'll go to the ERC20 test. I'm gonna comment out one line, right? If it's TDD, it should fail, right? So let's test again. All right, so something happened, right? I can change it back. So maybe I can change in ERC20 to make it fail. That might not be easy. Or I can. Right, I can make sure that it doesn't compile, right? So I can probably instead of plus, I say no. Okay, I can build. Oh, what's going on? It does more than I wanted. All right, because I changed the operator here, it should fail at some point.
It's cool.
Forge test again, right? This one should fail. This is demo. Yeah. All right. So something happened. So all right. And that's a quick demo about the project structure. So I can define build units. I can build modules for the smart contracts, and I'm gonna just show last bits because I said that there's different interpreter, right? So how about I do a repo demo. Set up. All right, I can print the functions. I can print I can use an interpreter that generates U code, so it generates this intermediate language that has another compiler, right? So I can also using another interpreter which actually visualize it in some sort of graphics diagram, right? So I can actually visualize the same thing in a different presentation, a different view. So Okay, so that's a quick demo, but how it works, right? So let me just now go to a little bit. I'll try to avoid the too deep of a theory part, which I'm not that familiar with anyway. So first of all, what is Solidity U? I mentioned it without explaining it, right? So Solidity compiler is called a SOLC, the Solidity compiler in short. Hence the project name is Yolc, so it's a play of a word. Solidity compiler also support, the U is it's an intermediary language, so it's not Solidity. Solidity can compile the U to the bytecode of Ethereum virtual machine, right? Okay. So first of all, the UCAT data type is actually a GADT. So if you know Haskell, you know what I mean. Otherwise, just consider it's a data type that has a little bit more general, a bit more general than the ADT you are familiar with, right? So look at the definition has three parts. One is EFF. For today's talk, I'll just ignore that. And the other is A and B. Well, basically, A is input type, B is output type. So that's kind of the type in general. About the UCAT, U as a category. But let's look into a few constructors. So it started with the basis of a category. You need an identity constructor which goes from A to A, right? So I have two representation on the top part of the diagram. That's something that you probably see from more often, right? So UID means identity is from A to A, right? I have another representation in the bottom. Instead I represent not the node, but I use it boxes. So it's just different way of representing it. The other thing that is a composition. So if you have a box called A to C, so if you see the right bottom part, you have it embeds two boxes. One is A to C, the other is C to B, right? So with that, intuitively you can compose them together, become having an outer box called A to B. Or commonly people use the top right view, right? So you have a function F, which is A to C, A leads to C, and G is C leads to B. Then you can intuitively compose them together. Usually you see it's a G after F become A leads to B, right? So the top one and the bottom one are the same thing. I use the bottom one throughout the talk, so because it's easier for me to draw some of the visualization. So this is a basic part of the category. So you need identity and you need a composition.
What is the SCSS?
Yeah, so in the previous slides that hopefully we can ignore that today. I don't have time to go into that. Yeah, okay. Actually, I use that to distinguish the pure computations versus the effective ones. So I use it for some purpose, but I think today I will skip that. Yeah. Okay. So as I said, explaining previous slides already. So A to B is also called a morphism in the category. But I'm gonna and A and B are the objects of the category. But for today's talk, I'm gonna gray it out. It's not important. A category must have a identity morphism for each object and morphism compose with each other. And I say it's intuitively. Yeah, I'll use a diagrammatical view throughout the talk. So there are other constructors, but I'm not going to show the code. I'll just show a bunch of diagrams. Hopefully, it's going to be more intuitive. So we already see the identity and the composition, the first two, and F cross product of G is actually part of something called a symmetric monoidal category, I believe. So you have, let's say you have F and G as separate diagrams. You can actually put them together, become one diagram. So that's F cross product of G. And then you can use them as one component. And alpha and alpha cap is actually for associativity intuitively, right? So the first one is first A and B associated with a C, right? You can actually swap the associativity according to the associativity law. So you make the A and B and C. So the brackets become the second part. So that's the alpha, right? The other one is opposite. So that's for associativity law. And sigma actually means swap, I guess. So you have A and B, then you swap the Y, become B and C. right? And you have a row which generates an empty. So this dash line means a unit or a terminal object, I believe. So you have a, you can generate a terminal object, or you can take terminal object as an input. So it's kind of just flip the image. You have eta eliminating the input. Maybe that's why it's called eta. And then you have a pi. So pi means that you have two inputs. You take the pi 1 means you take the left input, if you look this way, and pi 2 means you take the right input. And then you have the, I think this is kind of one of the most important ones. You have the delta, which is actually means duplicate. So you have one input, you can duplicate it, so you can use twice, right? So why we need all these, the other one, the last one is the fork. So you can have one signal, you can fork it to two individual parts of diagram, which is F, and you have G. F and G has the same input, and then you put it into one diagram called forking F and G. So why we do this? Because this is not doodling on paper, right? So we want to actually make the diagram very, very formal. So that's why all these little combinators, sometimes, you know, why can't I just cross a wire, right? But you can doodle on paper, but this is not doodling. This is a mathematical definition. That's why we all need these little combinators to actually make them formal, right? I think I need to be careful with the time. So, okay. The last thing is another category called a Cartesian closed. So we actually probably deal with in functional programming a lot, but we don't usually talk about it. Right? So the first one is apply. So if you have a function of A to B, and if you give A, you get a result of B. So that's a kind of application, right? So A to B as a function, and you give A, you get a B, right? And you have a curry, right? Curry means that if you have A and B, which leads to C in a box, you can wrap it up and say, I'm going to transform it into something else, which is A leads to a function object called B to C. Right, so this allows you to encode function objects such as A to B as a function object in the category. So that makes it a Cartesian close. All right, the last bits. So these are the non-category verbs. So in order to make this so you actually do something useful, so I have to actually encode something that there's no categorical stuff, right? It's just specific to your machines. So you have a storage operator like a storage get, storage put. That's very Ethereum specific. And the message calls. Ethereum allows you to do message calls, so you have to have those like call, right? And there's control flows, which I don't know what's better mathematical structure. So I have a bit more ad hoc stuff like switch statement, allowing you to have branching the code. You have a tight loop for foldable, stuff like that. And with these quote verbs, then I can actually make the ucat as a data constructor, sorry, as a type, actually useful. So that's a quick overview of ucat as a category. So now we talk about how can we actually embed Haskell code to the category. So I use a couple of techniques, and they all have some pros and cons. First of all, I can now define pure functions. All right, so I have just give two examples. One is a simple function f, which does x plus y. So all I do is define the type signature of f. F is a pure function which takes uint 256, another uint 256, and generates another uint 256. So I just do x y plus y. Can't be more simple than that. So the other is a sort of if then else, because the first type signature actually hides a lot of details, right? So actually, if you look into it, I'm working with for all R, because I don't care about which R is it. So it's R to A. So categorically speaking, I believe the anything to A is called contravariant, some sort of home functor. I'm going to ignore that. I'm going to go into it individually. Each is a set of diagrams of the same output, so anything to A, right? That's individually, and together they share the same input R, right? So that's for example, if you look at the if then else, you have the Boolean to B and B and B, right? So if the Boolean is true, you take the first diagram. If its Boolean is false, you take the second one and you generate another one. So this using the switch actually statement. So that's why I say together they share the same input R, but individually they have it's a set of diagrams that generates a Boolean, right? So think intuitively, I would say maybe think of it as a sub-diagram of the same diagram, right? R as a context. careful. So pros, working directly with objects in the category allows you to forget about the categories under the hood, so you can actually program it without thinking about it as actually a category in Haskell. But it has very big consequences. So sharing in this case is very tricky because it makes you feel like, oh, are you working with variable? No, they are not variable. They're actually a whole diagram. You actually, if you using the look like variable in Haskell, if you're using twice, actually there's no sharing, right? So you actually create duplicates. Because of this problem, you cannot use these for side effects. You don't want to duplicate the side effects unknowingly, right? So I'm showing you, so a case where the sharing is a problem. Remember that I can visualize what the diagram generated. So if I have a, b, c, which I do a plus b, blah, blah, c, generate something called a z. You would think z is a variable if you really think it's Haskell, but it's not. It's actually two diagrams. So if you multiply by z and z, you get a diagram duplicated. That's not great, right? If you do that too often. But it's kind of convenient. So there's a way of bypassing manually to kind of take the output and duplicate it, right? Because we have duplicate as a verb in the Cartesian category. So that's one way to do it, define pure functions. And the other is something that I really like. It's work by somebody else that it's called evaluate the linear typed function. It's not linear algebra, linear functions to symmetric monoid category. The reason we build a whole symmetric monoid category is because we can evaluate now the linear typed functions to those almost mechanically. So there's a library made by others, not me, and I can just convert that, right? So, but quick introduction if you didn't know yet what is linear type. So a function f is linear if when its result is consumed exactly once, then its argument is consumed exactly once. That's a regular definition, but intuitively, it means that every branch of the definition of f, its argument x must be evaluated, must be used exactly once. So that's the kind of definition I took from the Haskell's documentation. All right, so why is that useful? Before that, I first just show you a couple for a few lines of code, Haskell code, how to define linear functions. So G is something that we're all familiar with how to define Haskell. It's a simple A type to B type, right? F is the linear typed function, so they use this %1, meaning that A can be consumed exactly once if B is consumed once. And they have a Unicode version of it, so F prime is actually using the Unicode symbol. So I'll use that for brief because slides is smaller, right? So it's also called a linearity on function errors. It can manage uniqueness of the resource, like a Rust. I do believe that it can do more in Haskell, so I'm not gonna be able to back it up today, but I'll show you a demo in the end, how I use it. Right, so the magic is here. So there are two functions provided by that library. So it can convert A leads to B, which is a category. You saw the diagrams. So I use a symbol just to make the code shorter. From this left side, which is a category, from the right side is actually a linear function lambda. So it's from type A to type B. There's a prefix. I'm not gonna go into that today, but it's a linear typed function in Haskell. So A to B, that's encoding from a category to this linear typed lambda. There's a opposite direction which you can decode a linear typed function to a category, right? So the pros, it kind of solves the sharing problem automatically because when you express things as linear typed functions, you cannot use the output twice. You have to do explicit duplicate, and that duplicate, the interpreter can simply say, okay, we're not going to duplicate the diagram. We're just using the output directly. So that kind of solves the sharing problem, but in a way that forces you to do it. Yeah, I do believe it can encode some linear type timing temporal logic there. But the cons is also notable. So using linear types is not necessarily very ergonomic. And more importantly, we don't really use linear type for like Rust use. When we're not dealing with memory here. We're not dealing with any resource uniqueness here. So, right, so we really want a linear type for encoding some logic, but that's the con. So just show you that how the sharing is automatically solved. So previous code I changed to how you define the linear function, right? So instead of say z multiplied by z, I say okay, I'm gonna duplicate it explicitly. I can then do the multiplication, right? So then the diagram becomes much simpler, right? So there's no more duplications, really linear types, and you cannot bypass it because linear types forces you to say how do you want to use z again, right? Okay. Right, I still can make it. So I'm gonna show you the last bits of the talk, which is experimenting linear types, something called data versioning. Disclaimer, my approach is highly experimental. I'm still experimenting a lot of things, so I don't have a lot of papers to back up all my claims yet, so just take a grain of salt. I'll start with just a demo. So I'm gonna show you I'm going to switch to back Emacs. All right, so what's going on? All right, so currently everything works. So I'm just explain this part of code, minting function quickly. So it takes a balance called balance before. It calculates what should be the new balance for the mint target. The new balance should be x plus y. Basically, you say I want to mint more token to this destination called 2. I store the result, and I call something in Ethereum, which is very dangerous. You call untrusted function, external contract, and it's very it may do side effects, right? So far so good because you update it before you call the untrusted source. What if I swap the order, right? So it looks innocuous. I mean, if in other programming language, you probably wouldn't notice anything. In fact, there's a lot of real-world loss due to this kind of error. So I swap it, and I have a type error here. I'm not going to show you yet, right? So what's going on here, right? So the thing is, when I call external contract, because Ethereum computation model is too powerful, this one actually can trigger side effects. So whatever the value I get, the balance before, might get outdated, right? So the balance before, after this one, might be outdated. And the way I did it here actually detect that problem because you're updating the value of new amount, which is depending on the balance that can be outdated. So let's save the file and see what compiler says. Error. As expected, it says outdated data version. All right. So compiler actually helped. All right. So yeah, just to recap, what happens is that because it's actually qualified user, there's something called graded monad behind it. So each one actually implicit track what's the state of the world. So it's version 0 or version 1 or version 3. Whenever you get data like this call, the data is actually implicit in the type. So I can actually show the type so that it becomes less. So I can say, okay, tell me what's the type of amount. I can use this and say this, right? Then Haskell will gladly print, GHC will gladly print the type of it. So I'll show you the number here. So, the first wildcard. So new amount actually has a version called 0, right? The actual type is an integer with 32 bytes. And the whole monad, which I also put underscore, it's actually a monad say I want to go from 0 to 1. So now it works. So that's how. So the monad actually has a tracking the version of the world, and each data type you can actually version it if you want, right? So that's how it works. That's a demo of that. So I don't think I had all the time to explain all this, but just very quickly. So what is linear time temporal logic, right? So there's a great video if you want to watch later. There's a YouTube series I found that explained the LTL pretty nicely. Basically, on top of the logic, you have a few more temporal logic operators, such as you can express until, when, next, what should happen, or something always should happen, or something never should happen, or something eventually should happen. right? And with this, you kind of can model the programs as something called a labeled transition systems. You can think of them as state machines, although not quite, and or something probably more familiar with you, the FSAs, right? Finite state automaton. I think they're kind of all related, but don't quote me. I'm not a theoretician. So, all right. So, what I really want to do is somehow I can do model check of these LTO stuff, right? So, one thing in smart contract space, what you really want is first of all safety property. Something bad must not happen. How can we achieve that, right? So, and another thing is the liveliness property. Something good must happen. It would be good if something you want to happen, it never happens. So these are the basic property that, with the help of LTL, probably you can achieve that. Of course, I haven't achieved everything, so I only have the first example, which is I call it a linearly versioned monad. It is generally called a graded monad. Fortunately, Haskell has so much expressive type system. I actually can encode such a non-standard monad with a qualified do syntax. So this monad would if you ignore the first one, there will be basically like a state monad, right? You have a CTX, which is a context, which is state, and which returns an A. So this is a monad that has type changes each time you use it. So when you each time bind, the monad actually may change type. So VA, VB is a version of the world. So when you have a VA less than VB, so version always grows. And when you bind to a VB less than VC, you have a proof automatically, because transitivity, you have VA less than VC. Right? So that's kind of the bind operator. Pure is rather trivial, so you can bind a value to any version you want, right? Because it's from V to V. So thanks to Haskell, I can actually do that. So yeah, it's just one simple application. I'm still looking into other approaches, how people encode more complex state machines or in Haskell, and hopefully someday I can get somewhere. Or maybe my approach is not the best, so I have to look into that also. Yeah, next steps. Feature completion. I can't build all the Ethereum smart contracts yet, but I got a lot of things done. So I believe in the next few months I'll get something, get the feature complete, so that I will use in production for some of my company's side applications. I wouldn't use for the entire protocol yet. So I do believe the dog fooding culture, and I think many companies, especially like Superfluid, will build a protocol for other people to build application on top of it. I think dog food is a great way to test your own technology before you tell other people to use it, right? So I do strongly believe that culture. This is something that I'm still learning. I think I want to make a case for using linear types in Haskell to encode more types of labeled state transition systems. I looked into the prior work. One of them is called CREM. It's a package from Twig. It does type safety of state transition part, but they don't have the type safety on the vertices. So some of the things that like data version I did there, they can't really encode that yet. So I've communicated with the author of the CREM package, as I think there's some cross-pollination, if that's the word, there. So I look forward to actually expand more of my knowledge and apply it to the thing I'm building here. Yeah. That's all I have. So please start the GitHub, follow my work, and if you want talk to me directly, feel free to consider to join the Matrix channel. It should be available on Yolc Dev, and on X I also have an account. Not many followers, but I'm still building it. So either visit yolc.dev, the website, or the linktree.yolc. So transcript also available from the mono repo. So thanks for listening.
Thank you, Miao. It was a really interesting talk. I think we have maybe a few minutes for a Q&A. So if anybody has a question, okay, I see one.
So your Yolc get type was parameterized by some effects that you can have. But then when you showed the example of like putting and getting from the state, you said those are like the non-mathematical verbs, so they are actually included in Yolc. But I thought those would be the effects. So what are the effects if not those that you are parametric over?
Yeah, good question. So actually I glossed over, I didn't explain, right? So actually I have some constraints say that sget should only work for effects that is non-pure. So I at least constrain that.
Oh, so your effects are just like tags on a finite set of possible effects. They're not like fully extensible.
I can classify them, but the way, but you can actually probably build a effect system on top of it. But I just haven't. I only do the classification. I can say because for me it's important to distinguish things that have side effects or things that doesn't have a side effect. So I classify the EFF at least. But if other people are interested, they can probably build some effect system on top of it. But I'm not so sure yet myself. Yeah.
Thanks.
Okay.
So you spent a lot of time talking about the nice idea of using category theory to structure your compiler. And Connell Elliott wrote about that in ICFP back in 2017,
Yeah.
but you didn't mention him. So can you say what the relationship is between what you've done and what he's done?
Yeah, so I'm quite familiar with his work, and sorry if I didn't mention. But what I don't use is a compiling to category because I believe his approach is a GHC plugin which natively compile the categories, which I don't do compile to category. I would like to do, but I just didn't have time. So what I do is literally, without any plugin or anything, simply encode the categories as sort of Haskell code directly. So yeah, but I know what. So Connell Elliott has a paper called Compiling to Categories. So I actually learned a lot of things from his work. Yes, I should actually mention his work.
So why didn't you?
Why didn't I? Actually, if you go to repo, I mentioned his work. Yes, the repo I have README. I mentioned I referenced his work, not in the slides.
Okay, it's a good idea to mention the people whose work you build on. And you also mentioned the work by Bernardi and somebody else.
Yeah.
It was on your slide,
Yeah.
but you didn't bother to say it out loud. These people do a lot of work. You're building on it. It's very important that we build on each other's work.
Yeah.
Right?
Yeah.
That's absolutely vital. And so it's worth calling out, not hiding it. I think developers often think this isn't important.
Yeah.
So somebody who comes from academia, I want to tell you it is important. Please do it. And of course, I'm not just speaking to you. I'm speaking to everybody.
Yeah, thanks for critique. I just speak too fast and I kind of glossed over. But I in the slides, if people watch the video, they should see my reference there. Yes. But for Connell's work, yes, because I don't use compiling the categories, I didn't mention the slides directly. But in the README of the repo, I have everything referenced. Yeah.
Yeah, so meta question, what do you think is the main benefit to the end user of an Ethereum smart contract?
Sorry, what's...
What benefit of your work is the end user going to get? What do I see as the outcome?
Yeah, I think the tagline of Yolc project, I think it's really provide safety. I really want to give Ethereum smart contract builder the safety. I want to build some safety feature in the Yolc there.
But what safety features?
So data versioning is one of the features that I experimenting with. The other is at least you can separate the stateful function versus a pure function. That's I want to actually get more out of it for the Ethereum community eventually. Yeah.
But you're not demonstrating, for example, that preservation of value. So can you demonstrate that a contract doesn't lose money, for example?
Yeah, so the data versioning, I should have explained in more detail, but so data versioning is prevents a class of error in Ethereum called reentrance error, meaning that you invoked some side effects from external contracts, and they somehow call back, and they change some state, and somehow that actually has real world implication. A lot of contract bugs because of that. So I think data versioning can prevent that. So yeah, that's one.
That's kind of double spending, as such. You're spending the.
Yeah, could not quite, but there are. That's similarity, I would say. Yeah.
Thank you. I think maybe one more question. Okay, so thank you, Miao, and let's give one round of applause.
Yeah.